Hey guys, as promised, we are going to review potential energy diagrams. So to start, we're going to talk about what potential energy is. So potential energy is the amount of energy stored inside of a chemical substance. So when we talk about things like diatomic elements and compounds, the energy is stored in the chemical bonds. So looking at this reaction right here, our reactants are hydrogen and iodine. They have a specific amount of energy stored in the bonds that hold the two H's together and the two I's together. So together, if we add that energy, we have a starting amount of energy that my reaction has. We end with a different amount of energy. There's going to be a different amount of energy that's stored inside of my product. So you may say, I thought energy can't be created or destroyed. It's not. Remember that it's being transferred. Okay, so potential energy is being transferred to heat energy, and heat energy can be released to the environment. Okay, so looking at a potential energy diagram, we're going to have potential energy on our y-axis, and it's going to be measured in joules or kilojoules. Sometimes you'll see the unit calories, but we're not going to focus on that. We're going to use joules. Then you're going to have your x-axis showing reaction pathway or reaction coordinate. It just is showing you the progress of the reaction. So as this reaction progresses, what is the change in potential energy? So you see that the diagram starts with a certain amount of energy. In this case, 50 kilojoules of energy or stored potential energy. It ends with 100 kilojoules of stored energy. So we say that when we read our diagram, we read from left to right, and that's called the forward reaction. Unless they say otherwise, we assume we read from left to right. So the forward reaction here is represented by H2 plus I2 plus 53 kilojoules of heat produces 2HI. So here, this would be my starting amount, which would be my reactants. How much energy do my reactants have? Here would be my ending amount. In this case, 100 kilojoules, which would be my product. What do my products have when they end? How much energy is stored? So the way we read these diagrams, we can say the reactants have 50 kilojoules combined of energy stored, and the product has 100 kilojoules stored. We need to be able to show this using arrows. So over here, you'll see everything we need to know, and it's all color-coded. So we're going to show where we would put our arrows or where our arrows would start and end. So to show the amount of energy stored in the reactants, our arrow would be red, and it would be from 0 to 50. We can see that our reactants have 50 kilojoules of heat energy. Now, I placed it under the reactants, but remember that these arrows can be anywhere along this diagram. It could be all the way over here. But from 0 to 50 would still show me how much energy my reactants have to start. Okay, I'm going to leave it over here, but just make sure you remember it may not be where you expect it to be. Now, how much energy do my products have? Well, they have from 0 to 100. That's going to be the blue arrow. So I'm starting with 50, I ended with 100, stored in my products for the forward reaction. So what is this guy right here? What happened from start to finish? We didn't just go straight across. Well, this is representing how much energy was needed to be absorbed in order for the reaction to occur. The top of the peak, we said, represents how much energy is in the activated complex, this word right here. Now, it sounds crazy, but all it is a transitional state. As you're going from reactants to products, it doesn't just take the two hydrogens, split that bond, take the iodine, split that bond, and form HI. What happens is you wind up getting this complex, this transition state where certain bonds are not broken yet, and that would be your activated complex. So it has the most amount of energy in this diagram. We're going to represent it with this yellow arrow. So it has 250 kilojoules in this particular diagram, again from 0 to 250. Notice how all of these arrows touch the very bottom, or 0, of my graph here. The 0 would be saying 0 kilojoules, 50 for my reactants, 250 for my activated complex, and 100 stored in my products. Now, there's 3 other lines. So these next lines are going to show us what happened during the course of this reaction, which again is HI. H2 plus I2 gives me 2HI. So we said, in order for this reaction to occur, I need to gain 250, or I need 250 kilojoules. That's where the top of my peak is. But I already am starting at 50. So activation energy is how much energy needs to be absorbed in order for a reaction to occur. Well, you may think I would say 250. But remember, I'm already starting at 50, so I really only need to absorb 200 for my reaction to occur. If I wanted to show that in a line, I would have to start where my reactants are and have my arrow go up to the top of the peak. So that would be this orange arrow. Again, I can move this anywhere. This is still showing me the activation energy of the forward reaction. So we're more concerned with where it starts. It starts where my reactants are, and it goes up to that top peak. Now, we said forward reaction is going towards the right, so hydrogen and iodine forming HI. We can also say that this reaction is reversible, so I can also take HI and break it down back into H2 and I2. That is called the reverse reaction. For my reverse reaction, I actually am starting with my reactant, HI, having 100 kilojoules already. So if I need to get up to 250, I actually only need to gain 150 for the reverse to happen. So I start from my reactants and I go up to the top. So remember that for reverse, we're no longer going to call these guys products because we're using them to form something new. They're my starting material. We call it reactants. So you'll notice that the forward and the reverse don't have the same amount of activation energy. One way requires less energy than the other. The last thing that we have to know is heat of reaction, which we know is represented by delta H. Delta means a change in. So this delta H is telling us the change in, or the difference between the potential energy of my products, which we said would be here, and the potential energy of my reactants, which in this case would be here. So if we subtract 100 minus 50, we get 50 kilojoules. Okay, that's a pretty poor 50, but you get the point. So 50 kilojoules, and that's a positive 50 because we're absorbing it. 100 minus 50 is a positive 50. So 50 kilojoules are absorbed. If I wanted to show that with an arrow, it's going to be the purple one, and it's going to go from the reactants up to the products. In this case, up, because it's endothermic. It's absorbing energy. So the way we know it's absorbing energy is a couple of ways. We see that the products end with more energy than our reactant started with. It must have means that I absorbed energy along the way. Also, if they didn't give you the diagram, they may have just given you this equation. We look for heat, and heat is going to be my kilojoules. It might say energy. It might say heat. They may not give you a value. But if it's a reactant, it's going to represent an endothermic reaction. Okay? So let's do the same thing, but we're going to do an exothermic graph. So now, looking at this graph, you can already see the difference. For exothermic, the graph looks a little bit similar because it has this peak. I start off flat, I end flat, but you can see that your products now have less energy than your reactants. That must have meant that I lost heat on the course of this reaction. This reaction is actually represented by letters. A plus B produces C plus D, plus 20 kilojoules of heat. So if I wanted to show how much energy my starting reactants have, I would say 40. Where would the arrow be to show that? It would have to be up to 40, starting from the bottom. So we would think to put it here, but again, remember that it could be anywhere. It could be here. It could be here. So just keep that in mind. Where does it start? Where does it end? My products end with 20 kilojoules. I'm going to show that with blue, and it goes from 0 to 20. So again, potential energy is starting from the very bottom. Potential energy of my activated complex would be 100 kilojoules, which is represented by the yellow arrow here. So all the potential energies are represented, and they're all touching that bottom axis. Now I want to know, how much energy does the forward reaction need to start? Well, this is where my activated complex is. I need 100 kilojoules for this to occur, but I already have 40 in my reactants. So if my reactants want to form products, they only need to gain 60 more kilojoules, and that's represented by the orange arrow. And again, it could be here, but it's still going from my starting reactants, which is 40, up to the top peak, okay? For the reverse reaction, CD forming AB, now I'm starting with 20 kilojoules in my reactants, and I need to get up to 100. So I need to actually gain 80 kilojoules. So you can see here that the reverse actually requires more energy than the forward, which is opposite of what we saw with the endothermic diagram. So last thing we said is heat of reaction, which is going to be the purple. So again, change in heat over the course of the reaction. We started at 40 kilojoules, we ended with 20. That's a difference of 20. Now, remember that when we solve for delta H, we always take products, potential energy, minus reactants. So if I do 20 minus 40, I actually get a negative value. I get negative 20. Much better. So negative delta H would be for exothermic reactions. The negative just shows me that the energy was released instead of absorbed. So one thing I want to point out, when you look here, the amount of energy that was released, which is equal to delta H, has a plus sign in front of it. So we may get confused, but remember that when you're writing out a chemical equation, you would never use a subtraction sign or a minus sign, because the plus sign actually is worded or said as and. So A and B produce C and D and 20 kilojoules of heat energy. So how do I know it's negative? Because it's a product now. I'm releasing that energy. So just keep that in mind. So now what we're going to do is move on to what will happen if I add a catalyst in a situation, in a chemical reaction. What is it going to do to the potential energy diagram? Well, we talked about catalysts and how catalysts speed up the rates of reactions. Now, how does it do it? So if you're looking at this diagram, the dotted or dashed line represents the catalyzed reaction, so if a catalyst was added, and the bold line or solid line represents if there was no catalyst added. So normally, remember we said activation energy is how much energy this reaction needs to occur. Notice there's no actual equation here, but we should know that our reactants are represented first and then our products. We, again, assume forward if it doesn't mention reverse. So normally, I would have to gain from 65 to 90, which is 25 kilojoules. And notice how the arrow for that is over here. This is the activation energy of the forward reaction without a catalyst. Notice what happens with a catalyst. I start at 65, and now I only need to get up to 75, which is actually only a gain of 10 kilojoules. So the catalyst decreased the amount of energy needed for the reaction to occur, or activation energy, by 15 kilojoules, and that's why it can speed up and go at a quicker rate. Notice how this also happens for the reverse. There's no arrow for the reverse, so we're going to add it in, but the reverse would have to originally, without the catalyst, gain from 50 up until 90, so 40 kilojoules in order for the reverse reaction to occur. But with the catalyst, now it only has to gain up to 75, which is only 25 kilojoules. So again, 15 less kilojoules that are needed to be gained. So it actually speeds up the forward reaction and the reverse reaction equally. They both speed up and they occur faster. One other thing we need to know about a catalyst is what arrows are going to change when a catalyst is added. So we already talked about activation energy. The activation energy is definitely going to change. That's what a catalyst does. The other thing that it's going to change is how much potential energy that my activated complex has. It's going to now only have 75 kilojoules instead of 90. So anytime you have that word active, the arrows touch that top peak, those are the lines that would be affected by a catalyst. So hopefully, going through it nice and slow and seeing it, we're able to understand these potential energy diagrams better.